solar energy and the thermal energy storage. So today I am going to present this solar energy and different types of thermal energy storages. So here I will show you different types of technologies. However, I will not go into much detail about those technologies as well as some numerical models or experimental analysis. So here it is, the talk will be based on more or less informative type. Okay, so coming to the solar energy, we need to understand why we want to use solar energy. So first, solar energy is renewable and it is abundant in most part of the world. And third one is that it is CO2 free and basically it is environmental friendly. And for solar PV, whatever the operating cost is there, it is very low. Also, it can be used for off-grid applications such as for home, cluster of houses, maybe village, even cluster of villages also. Like in the power generation can be in the range of 200 kilowatt or 100 kilowatt to 15 megawatt or say 20 megawatt. Even we can go to the gigawatt also if there is a big clusters. Okay, and also we can use it for large scale electricity generation. So that's why we want to go for solar energy comparable to other types of energy like renewable energy, like wind energy, hydel power energy. Now coming to the Indian scenario, if we see, this is the report published by MNRE in the last year, in this year. So if you see that still thermal energy, basically thermal power plant is comprising of 63% of the electricity generation, whereas renewable energy has only share of 23%. And within that, if you see at the present scenario, wind power and solar power are producing nearly same amount of electricity. However, the projection of India in 2002 is that we have to produce something like 175 gigawatt using solar. So there is a huge challenge. Challenge is from technology development, and it should be understood that the advanced countries such as US or Italy or Spain, they have well-developed technologies, but we cannot just take their technology and implement here because the environmental condition, other scenarios are different completely. So we have to develop our own technology based on the requirement. So there are two ways we can actually generate energy through solar. So one is solar PV, which is basically a modular system. Efficiency at present is something like 15% to 16 to 17%. Whereas there is one more technology which is not very much very much well developed, but it can be developed, and the efficiency could be around 18%. And if we use storage, then the efficiency can go up to something like 22%. So there is a very good opportunity using solar thermal power plant, which is basically another type of thermal power plant where the source of the energy is solar, whereas in case of thermal power plant, the source of energy is fossil fuel. So, but there are certain drawbacks using the solar energies. So what are the drawbacks? We will see now. First, we understand that why we need energy storage. So this energy storage can be any form, like it can be electrical storage energy, it can be battery, whatever you can think. It can be fuel cell, it can be anything. Okay, thermal energy storage. But the main idea is that when there is no energy demand, so then we will store the energy in that storage, and when there will be an energy demand, then we will actually extract that energy from that energy storage and supply it and produce the electricity. And also, if you understand the economics, then you will see that during peak load, if we supply electricity, then we can charge a premium. So it's a win-win situation for this type of installing storage actually. So that motivates us to develop some sustainable type of energy storage. Now, among different types of energy storage, just I told you. So what thermal energy storage, is one of them. Now the question is why we should use thermal energy storage instead of say battery, instead of say the fuel cell, instead of other types of energy. Because in thermal energy storage the cycle efficiency is very high, something like in the range of 50 to 100 depending on the technology employed in the field. Okay, so thing is that main idea is that as solar energy or as you getting heat from the sun, so that energy you are not converting to another type of another form of energy. So you are saving the conversion. So that's why the efficiency is very high. Okay, as well as you don't have any, you are not handling any chemical, anything like battery or any fuel cell. So it is very much friendly to environment. Only you have to develop certain storage which can actually store energy during off-peak period, and when you require during peak period, you just extract it from there. Now there the challenges lies, and because of this, different technologies actually evolve. Now, why we need now thermal storage energy? I have plotted two DNI. The DNI means direct normal incidence of solar radiation. So one I have plotted for Greater Noida, something it was measured in the year of 2016, whereas another one is Udaipur. It is in Rajasthan, and here the variability in solar radiation is expected to be very low. So if you see, one profile is showing very drastic change. Basically, it's a cloudy day, whereas another profile is very smooth, and something like around 12 noon or 11 at 1 p.m. we get the highest DNI. So the difference here in two graph is that I have to develop certain technology in using thermal energy storage so that during cloudy days I can get uninterrupted constant power supply. Whereas in case of that Rajasthan, the sun, when the sun sets, the solar energy is not available. So we have to produce, if we want to sustain throughout the day, then we have to use some type of thermal energy storage which can be used during this night time to produce electricity. So you can understand there are two aspects. One is to remove the intermittency in the sun solar radiation. Another one is the availability of the sun radiation after non-availability of the sun radiation after sunset. So these two things we are keeping in mind and trying to develop thermal energy storage. Now, depending on the objective, the technology actually varies. Now, to give you some idea that how this thermal energy storage works. So basically, if we see that flat plate collector in many houses, I mean, the rooftop of house, you can see that there are solar heater. So where flat plate heaters are installed. So that is actually used to supply hot water to our for our household purposes. Now there also we can install thermal energy storage so that we can extend the energy extend the hot water generation throughout the day or maybe in the night also. Whereas on the right hand side, if you see, which is showing a typical schematic diagram of any solar thermal power plant, which is a two-stage solar thermal power plant. There we can see that if we install some thermal energy storage, which is abbreviated as TES, then we understand that during this cloudy days or during the non-availability of solar radiation, we can utilize the stored energy in TS and can maintain the electricity generation at a certain level, something like 100 kilowatt, 200 kilowatt, depending on our need. So basically, thermal energy storage is basically smoothing the supply, as well as it is actually bridging the gap between demand and supply. So that's why we can use this type of energy storage. Now, different types of thermal energy storages are there, and I will briefly describe all the storages. So mainly, these thermal energy storage are classified into three groups. One is sensible heat storage, second one is thermal heat energy storage, and last one is thermochemical storage. So sensible heat energy storage is well developed and means it is very easy to operate and very easy to design, and basically it can be useful in many places. Whereas latent thermal energy storage is slightly difficult, slightly complicated, compared to sensible heat storage as well. And then the thermochemical storage, which is the last one, is more complicated because it depends on the chemical reactions of certain materials. And from there we get the energy, which is very less developed. And now the thrust is on these thermochemical storages. So I will describe one by one now, and I will try to give you a brief idea on what are the different technologies available under this thermal energy storage. So requirement of any thermal energy storage is that it should possess very high energy density compared to the unit volume. Then the volume of the storage will be less and more amount of energy can be stored inside that volume. Second one is that the heat transfer between heat transfer fluid, which we will abbreviate it as HTF, and the storage medium should be very high, very good. So that when I need energy, I can extract the energy from the system. And when I want to store the energy, I can readily store the energy in the system. However, I will show you later that this is not very much improved thing, or we will not get like this type of thing in this type of storage. So third one is very much important, that chemical and mechanical stability of the storage. So we are targeting something like 10,000, 20,000 cycles of operations. Like if you think that one cycle is for one day, then you understand that 20,000 days you want to operate this. So yeah, there should be chemical and mechanical stability of the storage. And the next one is the reversibility of this material. Like you want to store it and then you want to extract it, so the material should be stable. Last one is the low thermal loss. So there will be huge loss to the environment of this heat. So we have to prevent, and if we are able to prevent, then we can store more energy basically. And last one is the ease of control, which is very much essential in any type of applications. So first I will start with sensible heat storage, which is basically depending on this principle, that is mass of the storage, say specific heat of the storage, and the final temperature of the storage. So if you are able to manipulate these three things, you are able to actually improve the sensible heat storage. So there are different types of storage, and accordingly it is classified into one tank storage and two tank storage basically. So under one tank, in one case there will be no phase change, like simple water is there, which we see basically in our solar water heater installed at the rooftop. Another one is steam accumulator, which is basically seen in the power plant, where this means this water and steam are heavily pressurized inside a vessel, inside a pressure vessel. So it is similar to our pressure cooker in our which we use regularly. And next one is in the classification is that you can put some material, some solid material inside this container to enhance the capacity of the storage, which we called basically a packed bed type of system. So this packed bed type of system can have higher advantages, but they have also disadvantages. I will show you later. Now there could be indirect storage system, like something like what I showed you, the two-stage solar thermal power plant. Similar to that, there could be a two-stage thermal energy storage. Like in one cycle or in one loop, you have one type of heat transfer fluid. In another loop, you can have another type of heat transfer fluid. Now there are also two-tank storage technology, which was earlier used heavily. Nowadays, because of the cost involvement, this type of storage has been is not used regularly. So people are now shifting towards one type of storage. Now going to our range of operation. So first one is very low temperature storage. So low temperature again is basically a solar water heater, which we use regularly. So it is as water is very abundantly available, as well as it is inexpensive. That's why you want to use. Another thing is that its specific heat is highest among all materials. So we use water. Okay. However, the main drawback, or I will not say the drawback, it has low thermal diffusivity, and because of this, many technologies have are developed, which I will show later. Okay. And another thing, when you use water, so it is, as it is not toxic, as well as it is not much corrosive in nature, so controlling is fairly easy. As well as you can mix some other materials with this water, something like nanoparticles, to enhance the capacity, enhance the thermal properties of this system. However, disadvantage is that if you use, say, water at atmospheric temperature, pressure, then the limitation, the limitation of operation is something like 100 degrees centigrade. Okay, at sometimes if you use normal the normal metal, then you will find that after some time, normal metal in the sense, this iron type of enclosure, if you use, then it could be corrosive in nature. So next thing is the high temperature system. So in high temperature system, if you see that the advantage is that, which I used to tell that, which I was telling, that steam accumulator as an example. So in steam accumulator, you can store liquid water as well as steam at high pressure, and when you need that steam, so you can actually open the valve and discharge the steam. However, the disadvantage here will be the steam, whatever you will get at the outlet of this steam accumulator, will be the saturated. So it will not be in superheated. So you have to employ some other technology to superheat it. Otherwise, this wet steam may cause many problems. Next one is, we can move from water to oil. So oil as heat transfer fluid has not been tested much. Okay, so means people now are trying to develop water as heat transfer, oil as heat transfer fluid instead of water. But basically, the operation range of oil-based thermal energy storage depends on the flash point of the oil. So something like up to 400 degrees centigrade, depending on the oil, you can use it for in a single phase. But as oil cannot go into two phase, it will burn. So you have, the limitation is around 350 to 400. So beyond 400, you cannot use oil. So there you have to use some other heat transfer fluid. Nowadays, molten salt is coming into picture. So molten salt can act as a heat transfer fluid. It can act as also the thermal storage system, which I will show you later also when I will go to the latent heat thermal energy storage, because it has some latent heat content also. So molten salt has many disadvantages, in the sense these are all basically chloride or chloride based salts. Okay, or nitrate based salts. So these are very corrosive in nature, and because of this, the container has to be well protected. The material is in question now. So and also if it is operating something like at 600 degrees centigrade or 700 degrees centigrade, then normal steel will not work. So there somebody has to employ or use Inconel or some other stainless steel grade, something like SS316L maybe. So, but the cost will be high at that high temperature. So now different types of material, as here I have listed down, like water we can use, silicon oil, mostly it is used, then transformer oil also used, then molten salt. One example I have given, which is KNO3, NNO3, 40:60 ratio, they are mixed, and depending on this ratio, actually the melting temperature varies. Okay, so another one is used as also sodium, even KNO3 alone also used in this type of storage, depending on the application, temperature application range. Another type of storage, what I was telling you, that in the container, you can put some gravels or rocks, any other type of, or any concretes, and to fill it up. And then actually this filler material will act as a storage material, because it has some specific heat. Now, it is very widely used actually, and this type of material or this type of configuration is very much um, very much applicable in chemical engineering. So they have very famous thing like packed bed system. So similar to that, we have also developed here something like packed bed of rocks, packed bed of say concrete, which actually a thermal energy storage. However, disadvantage is that when you use this graphite as filler material, so above 400 degrees centigrade, it requires inert atmosphere. Even if you use metal also, so the problem with metal is that metal has high thermal conductivity. Basically, it has high thermal diffusivity, but it has high weight. So because of that, the weight of the system will be very high. So that is one of the drawback of this type of system. And also, as if you are using metal, then the energy density will be lower because of the sensible heat of the metal is lower. Even it is lower than 100 joule per kg Kelvin. So but why we use metal, rocks, gravels? Because these materials are not costly. So that's why people used to use this type of material in this storage in the storage system. So now different types of material I have listed down, which can be used as this storage material. So something like aluminium, copper, anything you can think of. Concrete, graphite, even gravel, rock, riverside gravel, whatever you can think of, that can be used as the storage material. However, if we see this specific heat here in sensible heat storage, we have to see this specific heat value. So you can see if we use metal, as I told you, these are very low compared to water, which has something like 4.1 kilojoule per kg Kelvin. So that's why you have to now choose when you design something, you have to choose that which system you will use. It's a simply water-based system, or it is a combination of water or some filler type of system. Now another phenomena or another technology based on this thermocline system, what we call, or a thermocline phenomena. And this phenomena is actually happens in nature in the sense that when you see sea, basically means there the sun radiation actually fall on the surface of the sea, and the temperature gradient will form inside along the depth. Okay, so there because of the density difference, you will have because of the temperature gradient, you will have a density difference, and you will see hot water will be at the top and cold water will be at the bottom. Now, if there is no disturbance inside this, say, sea or a very big reservoir, then you will see that a distinct layer of hot water will be at the top and cold water at the bottom, and there will be a sharp change or sharp interface in between them, so which is called thermocline. Okay, so here what you are trying to means get, what is the advantage of this thermocline system is that the temperature gradient at the interface is very sharp, and that what I was showing you, that AMCP and some temperature difference, the temperature difference will be very high, and because of this, that energy storage will be very high in these cases. However, there are certain drawbacks of this system in the sense that if there is disturbance, like water is coming inside the reservoir and going out the reservoir, then there will be a disturbance, and because of this, interface may not be sharp, then it may be diffuse, or it will, and also if the thermal diffusivity of this material, if the heat transfer fluid is high, then this interface will be more diffuse, then you will not get very high temperature gradient in the system, and because of this, that performance of the system will reduce. So our main always objective is that to how good we can maintain a sharp interface, and if something is coming in like heat transfer fluid, hot heat transfer fluid is coming in and cold heat transfer fluid is going out, or rather cold heat transfer fluid is coming in and hot is going out, so we have to ensure that interface should not be disturbed, and accordingly this design changes, actually that thermal energy storage design changes. So some little bit of modeling I just show you, that consider a cylinder which we can actually model using an axisymmetry boundary, axisymmetric domain, and we employ the heat loss from the boundary, and inlet outlet is there, and simple equations we solve like mass, momentum, and energy equation along with the turbulence model, and we can find that if we do some experiments, we see that our model can predict this performance very well. So these type of models can be used to analyze this type of system, and which will help you to develop the final design of this system. So coming to the next part, which is the latent heat storage. So here you see that we have MCP delta T, but plus some other term, which is basically mass of the material plus latent heat. So some extra term is coming in latent heat storage compared to the sensible heat storage. So that's why we expect that the energy density is high in latent heat thermal energy storage. So how this storage works? Basically, this idea means this phase changed material based method. We know this thing from our 7th standard. Something like when there is, just take one paraffin or candle paraffin, whatever you can say. So now it is in ambient condition. It is in solid state. Now you heat it up. Now what will happen? The temperature of the material will go up, and it will reach its melting temperature, and then once the melting is completed, it will again rise. The temperature will again rise. So during melting, so there will be some latent heat of fusion. So that we want to utilize here. So now I have cited one example of paraffin, but you can see for water also. So water changes from solid to liquid, means ice, and again liquid to vapor, means where we actually get the boiling. So each stage it has some latent heat of fusion, and we are targeting that. Now in case of pure phase change based material, so that solidification as well as melting will occur only at a constant temperature. Okay, so which is called melting temperature. Now if it is impure material, then it will, that melting will occur over a range of temperature. So starting melting temperature will called as solidus temperature, and final melting temperature will call as liquidus temperature. So here I have shown example for solid to liquid, but it can go from solid to gas, which is in case of camphor, and liquid to gas also, like water to vapor or steam, you can say. So now what are the advantages? First one, I have told you that advantage is from the energy storage, means it has very high energy density compared to sensible heat. Also, if we go through some other, go through our second law efficiency in thermodynamics, we can say that even from that second law of thermodynamics, that the efficiency, second law efficiency will be higher in case of this latent heat thermal energy storage. However, what are the drawbacks are that it is expensive compared to sensible heat. However, that's why it also it needs special attention while selecting the material, so which I will now describe briefly. Now, what are the selection procedure for phase change material? Always we look for two criteria. Like first one is the application temperature. Like if my application temperature is say cooking, so which is needed at 150 degrees centigrade. So I have to select some phase change material which will have melting temperature something in the range of 130 to 150. Now also one more thing we have to understand, that as we are utilizing latent heat of fusion, so that means I need the high latent heat, means I need more energy stored as in the form of latent heat. Other properties of ideal PCM are that it should have high thermal conductivity, should have high specific heat, should be chemically stable, non-corrosive, and should be non-poisonous, non-flammable, non-explosive. However, all these properties are not available in any material. So now the research actually starts from here. So another drawback of this phase change material, most of the phase change material actually possesses very low thermal conductivity, something like 0.2 to 0.2 watt per meter Kelvin. So which is basically act as an insulator. Okay, so if you see glass wool, which has a thermal conductivity of something like 0.04, it has only one order magnitude higher than that glass wool. So it's more or less acting as a insulator. So the first technique we employ is that how to improve this thermal conductivity. If we able to improve the thermal conductivity, then we can actually exchange heat between heat transfer fluid and this material efficiently. Otherwise, there will be a very high thermal stratification inside this material. So, and that's why it requires very high thermal conductivity materials to be inserted, like aluminum, copper, stainless steel. We insert in this type of material. So we actually here we cannot increase the thermal conductivity of the phase change material. Rather, what we are trying to do, we are increasing the overall thermal conductivity of the storage. So there is a certain distinction between these two. So as thermal conductivity is the property of the system, so we are not able to change that. Rather, we are changing the changing the thermal conductivity of the storage basically, which I will now describe. So now, depending on the type of phase change, there will be the types like liquid to gas, solid to liquid, then solid gas, solid type of phase change. So mostly what we use in thermal energy storage are solid to liquid phase change or solid to solid phase change. But we don't use much liquid to gas and solid to gas, because gas, when you use gas phase, gas transition or gas transformation, there will be a problem of storage, as gas requires more volume to store basically. So that's why we only concentrate on solid liquid and solid. And now under the solid and solid liquid, you will be seeing that lot of materials are available. So under solid liquid, you can see organic and inorganic materials are available. Organic means it's a paraffin based material, what we usually use in daily life, like paraffin, any other types of material means called paraffin based material. Another inorganics are salts, like KNO3, NNO3, hydrated salts, all types of alloys also we can use. Now in case of solid, we can use polymeric type of material. Now, depending on the operation conditions, this phase change material is also categorized into low temperature PCM, medium temperature PCM, and high temperature PCM. And depending on this, different materials we can use, like low temperature is ice, water gel. In medium temperature, hydrated salt, organic like paraffin based material, polymeric material. And high temperature application, something like 300, 400 or 600 degrees centigrade, we have to use molten salt or metal alloys. So some typical example of materials having different melting enthalpy or latent heat of fusion. You see fluorides has very high latent heat of fusion, but we cannot use fluorides because it is toxic, as well as it is corrosive in nature. So mostly what we use is the organic type of material, which has latent heat of fusion something like 200 kilojoule per kg, or molten salt, which will have thermal latent heat of fusion something like 100 to 150 kilojoule per kg. However, still now this chloride, carbonate and fluoride we didn't use because of the material issues and toxicity issues. So some example I have listed down. Like organic on the left hand side, it is showing like paraffin, RT42 are the commercial name of the paraffin, one of the type of paraffin which is manufactured by German company, and some A164, which is again commercialized phase change based material. On the right hand side, if you see, it's a molten salt based material, and the left hand side, right hand side corner, the table shows that palmitic acid, some type of acid also you can use for as phase change based material. However, only concern you have to see in this type of material is what is the latent heat of fusion basically. So now it's a nice chart which is showing that which one has good properties, or what properties this type of material possesses. Like salt hydrate, just for example, if I see the thermal conductivity is high, but its corrosiveness is also high. Density is high. Density means if density is high, that means its weight will be high. Okay, and it has very high phase segregation. Means if you see two materials are actually mixed to form one material. Now when you put in a cycle, like one thermal cycle means you are heating from one low temperature to high temperature, again bringing that material to high temperature to low temperature, you will see that phase will segregate. Okay, so and because of this the properties will not be remain same. So again you have a big issue while deploying. So now the paraffin wax don't have any phase segregation because it's an organic based material. Although it is a combination of hydrocarbons, but it is relatively very highly stable actually. However, the main problem with paraffin is it has very low thermal conductivity as well as it is flammable sometimes. Okay, so other than that, it is very good material. Now, fatty acid, people right now, at present, they are investigating this thing, which has very high density, little bit corrosiveness is there, but phase segregation is not there. And one more important point in thermal phase change based material is that supercooling. So what is supercooling? Supercooling is that the material can, or the liquid of the material can exist as liquid below its freezing point. So which is called metastable state. And because of this, some problem arises. Okay, so that is one of the biggest problem in this salt hydrate type of material. However, paraffin based material doesn't show this type of phenomena basically. Now, there is some comparison between organic and inorganic in the sense that the organic material is available something in wide range, something between even minus 2, actually 200 degrees centigrade, minus 10 or minus 5 degrees centigrade, 200 degrees centigrade. Also in inorganic, you can use it up to something like 500 to 600 degrees centigrade. Now, metal eutectics are basically metallic substance where we are using eutectic compositions. So the main advantage is that it has very high thermal conductivity. However, it has very low latent heat of fusion. Actually, because of this, the eutectics are not very much used. Now, where I should put this material? So this phase change material. So these are different types of container are used in this type of thermal energy storage. Okay, so and this is where from the research starts actually. So now see that there are basically I have given only the main containers for geometry. One is called shell and tube based container, which is showing here. Second one is that this packed bed type of storage, where earlier I told you that we fill this container using gravel. Here we are not using any gravel, rather we are using phase change based material or PCM, which is actually kept inside a spherical capsule actually. Okay, so that is poured inside this container. So in the cell and tube heat exchanger, you can see there is one example which is called a multi-tube heat exchanger. Okay, where in the shell side, phase change material is kept, and in the tube side, heat transfer fluid is flown. Okay, opposite is also done. Like PCM is also is kept in tube, and heat transfer fluid is flowing outside inside that shell. So depending on the application, these configurations are chosen. Okay, so now because of certain issues in phase change material, so when you design this container, so we have to keep in certain things in mind. So one is that how we can improve heat transfer between heat transfer fluid and PCM, and within PCM also. So there are two broad methodology we adopt. One is we can increase the heat transfer area, and second one is we can increase the effective thermal conductivity of the storage. So how we can increase the heat transfer area? Something like we can use some we can actually use many tubes instead of single tube, and where how we can improve the effective thermal conductivity. We can add some additives, something like graphene, something like aluminum powder, something like copper powder, or we can insert some extended surface which we call fins, or we can put metal matrix inside this container. So how it will what is the container, how the container looks like? So something like on the left hand side I showed you that the fin is attached on the tubes, okay, and the HTF is flowing through, or heat transfer fluid is flowing through this tube, and outside this or in the shell side PCM is kept. So one example is longitudinal fin, another one is annular fin, and third, which is a metal matrix type of thermal conductivity enhancer, where we just put some wire meshing or mesh of wire basically. And we try to actually improve the overall thermal conductivity of the system. Now also we can add some filler material. It is shown like so people have used fiber cloth, fiber brass, even graphene, graphite, whatever you can think as a powder, which has very high thermal conductivity. But the major drawback of this the addition is that additive materials are that it can settle during the cycle. Means when the phase change material is in liquid, because of the gravity, these particles may settle down at the bottom. So which will again alter the thermophysical properties of the overall system. Now people nowadays also incorporate heat pipe on the heat transfer fluid tube surface instead of fin, and heat pipe has very high thermal conductivity. So that's why it can transport heat from HTF to heat transfer fluid to the PCM very well. So now one example that what we have developed in IIT Bombay, it's called multi-tube fin-based thermal energy storage. And we did experiments and we did some numerical analysis, and how the melting of phase change material progresses with time. We actually characterize that, and how long it will take to melt, we also find out. And the time required to melt the phase change material completely, actually the time of will be the time of operation, because after that there is no use of phase change based material. So once phase change material melts, you have to solidify it for its use. So some of the metal matrix type of thermal energy storage we have developed in our IIT Bombay lab, so which we have characterized experimentally and numerically using our the experimental loop, which we can operate something like 200 degrees centigrade, and one more loop is also installed which can be used for 400 degrees centigrade experiments. So now we also try to figure out how phase change material, what is the temperature profile inside in the phase change material by using thermocouples. We actually map and try to figure out that what is the profile inside this thermal energy storage. This is all our cylindrical type of thermal energy storage, where I am showing all the data in one plane. And then as I told you, that we also fill this container using some filler material like phase change based material. So that type of also thing we have developed here in IIT Bombay, and this is one experimental investigation we have done using steel ball as the capsules, and phase change material is kept inside this capsule, and we try to see that how long it takes to melt and how quickly it responds to the change in the system, which I will discuss at the end basically. So this is some temperature histories. We just put the thermocouples at the inlet and outlet and try to figure out what is the change in temperature because of this thermal energy storage. So basically, if you see that we apply a step change across this thermal energy storage, something like 200 to 200 degrees centigrade during charging and 100 degrees centigrade during discharging. Now we try to figure out what is the outlet temperature from the thermal energy storage. Now if you see this delta T is, if means during charging and discharging is small, then that thermal energy storage will be very good, because this thermal energy storage, that means able to stabilize the heat temperature fluctuations in heat transfer fluid, which is coming because of the change in solar radiation. So our main objective is to minimize the outlet temperature drop, actually drop between charging and discharging. So then that will be very much efficient. So now if we see the efficiency, how much we get from here of this thermal energy storage, something like 76%. Now if we optimize this storage container, then we can go something like 95%, which is very much needed in this type of thermal energy storage for deployment. Now last phase I came to my to my presentation, which is basically thermochemical storage. And here we utilize the heat of reaction. Now, what is heat of reaction? We all know about endothermic and exothermic. And during this endothermic and exothermic process, and heat of reaction will happen, or will generate, actually will come from this reaction. And we utilize this reaction to store the energy. Now, how we will store that I will show you later. Again, there will be some type of storage design. Now, what are the examples of this exothermic endothermic reaction? Like if you can use CaOH2 and then you can heat it, and then it will have conversion from CaO to H2O, and because of that heat you have to add, then that heat either add or you have to extract. So that heat you will utilize for storing basically. So something like SrBr2 and 6H2O also use as a material which can also be used for storing the heat. Now, what is, let me little bit tell you here, SrBr2 6H2O, it means this molecule SrBr2 contains 6H2O, and that 6H2O actually is inside the molecule of SrBr2. Now, if you heat it up, this 5H2O will go actually very quickly and evaporate actually, and 1H2O will be remaining, and at something like very high temperature, something like 100, not very high, like say 80 or 90 degree, if you again heat up, then one molecule also it will go out of the system. So now again, if you add here if you add moisture to this SrBr2, then you will again recover this 6H2O. Now now how many times you can do, that is also a great research actually. Now coming to this energy density. So if we see the sensible heat, if we see that for the same amount of heat storing, the thermochemical storage actually takes very small volume. So that is actually biggest advantage of this thermochemical storage. So we using a very small storage, very small container, you can store a very high amount of energy, which you can utilize for future use. So basic advantage, if you see, of thermochemical storage, that you can store energy for a very longer duration, even for 1 year also, which is not possible for any other type of energy. Okay, so if you able to insulate this thermal energy storage, means thermochemical storage well, then you can store that energy for even 1 year, 2 year, like that. So this is called a seasonal storage type of. So in France or in Spain, when winter comes, actually this type of storage is very will have very good application. Like during summer they store heat, and during winter they extract heat for say 6 months, 7 months. So this storage is very good in that terms. So now different types of mode are available. One is closed mode, another is open mode. So first one, closed mode, is that, so something like as it is thermochemical storage, you need one reactor. Okay, so in that reactor you will put that material like SrBr2, whatever you want, and you will supply heat transfer fluid through that. Okay, and try to remove those actually molecules, water molecules, from this molten salt. Okay, so now the thing is that when this 6H2O or 5H2O is releasing from this from this hydrated salt, this has to be kept somewhere. So there will be one condenser, and valve will be there, which will be opened during this charging process. And now when it comes to the condenser, so water vapor or steam will come, or water vapor will come inside this condenser. Now you have to extract it to make it liquid, otherwise there will be a containment issue. Now during discharging, what you have to do, again you have to heat slightly this condenser. Now this water will evaporate and go into this reactor, which is now SrBr2, whatever, it is not having any water. So this water which will coming from this condenser, it will again react with SrBr2, and it will again regain its own properties actually. So this is the mechanism, this is the way used to do. But the disadvantage of this system is you have to make a vacuum, you have to maintain vacuum in the system, so which is little bit difficult. And also Also you need a separate storing vessel for gaseous reactants. But this method is this mode of operation is useful for toxic type of higher salts basically. However, when you are not using any toxic type of salt or non-toxic salts, if you are using, then we can use open mode, where you just take hot air from the ambient, or rather you take air from the ambient, heat it and push it into the reactor, and the cold air, whatever you are getting, it can be exhausted to the ambient again. So it's an open mode. So there is no closed mode. The advantage is it can be operated at atmospheric pressure. So there is no leakage issue and no requirement of vessels are required. So it's an advantage from that point. However, only non-toxic material you have to use. Otherwise, there will be a difficulty in if toxic material are used. So now little bit different types of material I have listed down. So depending on the temperature range, how much energy density you will get, you can see. So if you see the values, whatever I showed you on the left hand side on the y-axis, you see the values are actually 1 order magnitude higher than the latent heat of fusion. So that is the biggest advantage of this type of material. And also that depending on an application temperature, you can get from 0 to 1000 degrees centigrade of different types of material in that temperature range. Although the people didn't try it, but there is a very good means wide range of material availabilities are there. So some examples of material are like MgSO4, CuCl2, CuSO4. These are all hydrated salts. Okay, and these hydrated salts are very hydroscopic in nature, and because of this, it will create a little bit problem, which I will describe now. So this is one phase diagram of NaBr 2H2O, that at what temperature, what will be the state of this NaBr and with 2H2O. So one during dihydrate, so if we maintain the relative humidity in this range and temperature range is 10 degrees centigrade, then you will get dihydrate. And then if the more water is added, then saturated solution. If you are heating it up, then anhydrous, it will go to the anhydrous phase. So this is plotted in this phase diagram. Some typical examples of this material: CaCl2, CuSO4, MgSO4 is widely used, MgCl2 and NaBr, the different types of material people have done. So some now how the SEM images looks like if I hit the at the beginning, when the material is as it is, the SEM image will look very nice. Okay, now when you dehydrate, so after dehydrate, you can see many pores are creating inside this salt. Again, if you even rehydrate, then this pore didn't disappear. Okay, or it didn't come back to A condition. So there will be issue of reversibility. So that is the problem of material. So we have to choose the material so that we can get back the original condition after dehydration. So there would be more problem like deliquescence, like it will be feel like watery. If you add too much of relative humidity or too much of water, then it will look like watery material. Or you can if you heat it up very high temperature, at a very high temperature, then it will be sintered, very powdery form, you can see it, which is a problem of this type of material. So then again, as one more example of hydration, that it will make a agglomeration also if you add more water. So some molecules of the salt will agglomerate and may be a form of form a big chunk of material. And if you have a big chunk of material, then you cannot utilize it for the next cycle, because you will not be able to extract moisture or extract water from individual molecules. That will be a big problem. So now also, if you increase the thickness of the reactor, there will be issue of heat extraction, because you are putting more salt inside that bed, and because of this, that there will be that because of this heat extraction will be a problem, because you will not be able to maintain uniform porosity over the bed. So because of this, you will not be able to extract water from individual molecules or salt molecules. So what are the proposed solutions means to overcome this? So increase the porosity of bed using metal foam, or use some type of other materials like extended graphite, some other material. Even silica gel is also used to absorb excess moisture or excess water actually. So these are the additives are added with this salt hydrates to improve the operational of this thermal energy storage. So we have done some analysis of this system, and you imagine that as a means you have a this covered, and within that almirah, within that several racks are there, and these racks actually are containing these materials. So we modeled it and then we characterize it, and we find that numerically we can predict the performance of the system well, but still there is a huge gap between experiments and numerics. Even very few studies are there in world actually that are conducted on this type of thermal energy storage. So this is a new field, and because the materials are not well characterized, and as well as the phenomena are not very well known, so we have to do more research in this field. So very broad way, the summary is that we can use solar energy for our country, but we need to develop certain technologies, and these technologies we have to understand that it is applicable to specific temperature range. So one design cannot be used for whole temperature range. So